Yeah, hello. Yeah, hi, good afternoon, everyone. Uh, so if you remember yesterday where we have left, uh, so we were doing the logistic regression cost function that we discussed the thing is the predicted y output, as you can see on the screen. I'll just made it a slideshow. Uh, Current slide, yeah. So okay, so here we have seen that the predicted output is the activation function sigma, and it was like w to the transpose x plus b for each and every training sample. And what we wanted is the ultimate outcome should be the predicted output should be very close to that of the ground truth. And there we have seen why we did not choose to use the squared loss, and instead we moved to the logarithmic loss. And then based on the value of these y 1 or 0, what actually we got like in the loss functions. And then finally we computed the cost function, which is nothing but the average of all the individual losses of the individual training samples. And then finally we got the expression which is shown here. We use the highlighter. Yeah. So next we will look how to view the logistic regression as a small neural network. So then we'll start from the gradient descent. So basically this gradient descent is used to by the backpropagation algorithm to update the weights, and we will see how we need to compute the derivatives to basically compute the gradient descent in backpropagation algorithm as an optimizer. And then we will see how we get into step-by-step methodology as to how we compute the gradient descent. Various variants of it are there, like the stochastic gradient descent. Okay, this is one of the optimizer. And Adam, okay, RMS prop, ADA grad, ADA delta, various type of optimizers are there, and stochastic gradient descent is one of them. So here we will see how it looks like, and what are the, this is basically the main engine of the learning process. This is very important. So let's pay attention to it. Okay, anyways, let me start. So Jagan, am I audible clearly?
Yes, sir.
Yeah, am I audible? Is my voice clear?
It's clear, sir.
Okay.
Can you speak louder, sir? I
Yeah,
think
yeah,
it's better.
yeah. So now is it okay? Now is
Yeah,
it
it's clear, sir.
okay? Whenever
Just
yeah, whenever you face any problem, you just let me know immediately.
sure, sir. Sure.
Yeah. Okay.
Just I want to recommend to faculties, please use your headphones, and the voice better will be clear for you. Please, I recommended to you morning also. Someone low voice. It's a depend on only uh, your network bandwidth. If your network bandwidth is good, you'll go without interrupt. You can enjoy the session. Okay. For audio, I recommended use headsets. Please. Thank you, sir. I'm
Yeah.
handing to you.
Okay. Thanks. Okay, so it's just a recap what we have seen as the y cap or the y hat. That is equal to the sigma of this WTX plus B. That is a sigma of Z basically, where Z is this equation what we are computing WTX plus B, and then we are passing that response through an activation function that is a sigma, and it looks like this, like 1 by 1 plus e to the power minus Z, which is basically a convex function. Okay, what we discussed yesterday. And this is the cost function J of WB, which we have seen in the previous slide. So now let's talk about how you can use the gradient descent algorithm to train or to learn the parameters W and B on our training set. So basically W and B are the parameters, and JWB is the cost function, which is shown here by this curve. This is a 3D representation. And our basically the main task would be to find the minimal value of the parameters W and B, the optimal value of the parameters W and B which minimizes the particular cost function j. That is our target here, the target of the gradient descent algorithm. So let's start with the initial seed value. Okay, this particular red thing, the red point you can see, let's start with the seed value, and it's a random value basically, and then step by step we will proceed, and our target should be to reach this global optima. That is the main idea of this gradient descent. We have to start randomly with taking a particular random value here or any point here, and then the final goal is to move step by step, is to proceed step by step, and then we need to move to this particular base point where this is the global optima, denoted by this global optima. Okay. Okay, so let's see how we do this. Okay, so if you see, this is a 2D representation of the previous 3D graph. So we need to repeat this process basically. It's a continue, like W colon equal to, I mean, we need to update W every time, because during this stochastic gradient descent, during this optimization process, every time the value of the weights gets updated, and we try to converge towards the final trend model. Every time it gets updated. So how it updates? Let's see, W colon equal to W minus alpha djw by dw. So this is the I mean the derivative is this djw by dw. This is the derivative. Okay, now this derivative is nothing but the you undertake this derivative to find the slope. This is basically the slope of that function at this particular point. Okay, so you have to find the slope, the current slope at this particular point, and then you need to determine whether you will go up or go down. So here you can see we need to go down to reach to this minimal point. Here also you need to go down to reach to this minimal point. Okay, so this is, we need to compute the slope, that means, and based on this computation, based on the value of the slope, we need to update the W. Okay, so so here therefore that is the W is colon equal to W minus alpha dW. Alpha is the learning rate. That means learning rate here means, suppose you are at point here, you need to jump to this point, jump to this point. Now how long you will jump, this period is determined by the learning rate. So here we need to choose an optimal value of the learning rate. We should not jump too high or we should not jump too less. So we need to choose the learning rate. So selection of the learning rate also plays a major role in how, as to how fast you are converging to the global optima. So we do this repeatedly until the algorithm converges to this global optimal point. So, so the thing is here, what is the slope here? What is the slope here? For say, for example, this particular point. So is it a positive slope or a negative slope? And also this one, what is it a positive or a negative? Okay, so here the thing is, this particular slope is a negative slope. It is going down, and this particular slope is a positive slope because it is going up. Okay, now the thing is, why this is called a negative slope at the steepest descent? Why is called a negative slope? Because if you see, as we go right, as we increase W, the value of this particular function, say for example, this is Y and this is W, this is J, say for example, this is J, the cost, and this is W. The value of this J decreases as we move, as we increase W, the value of J decreases, and here also, as we increase W, the value of J increases. This is decreases and this is increases as we increase W. So here if you see, if we increase W, the value of J increases. So that, for example, at this particular point of W, the value of J was this. As we move right, the value got increased of J. Okay, so this is called a positive slope and this is called a negative slope. Now, the thing is, while you are updating, so for example, I'm writing W equal to W minus alpha of a positive slope. Suppose I am at this particular position. So djw by dw is negative, less than 0. Okay, because the slope is negative here. djw by dw is less than 0. That means w, so here you will write w equal to w minus our negative slope. Okay, w equal to w minus our negative slope. That is, you can also write djw by dw as only dw. Just keep in mind that it is representation djw by dw, you can only write dw also. Okay, so that means if dw is negative here at this particular point, if dw is negative, that means what will happen to the w? It will increase. So w equal to w plus alpha into some particular positive value. Okay, so w equal to w plus something if dw is negative. That means w will increase. Okay, so w here it is increasing. So in the negative slope here the w is increasing. That means once the slope is negative, then we need to increase w to reach towards the final minimal point. In this way we update the w. In another other way, for example, I am at this particular point. So what is the slope? This is positive. At this particular point the slope is positive. Okay, so what will happen? W equal to w minus alpha of a positive value. So w equal to w minus something. So w will be decreased. Okay, once we update w, it should be decreased. That means while at this particular point I need to decrease w to reach to this global optima. So now don't get confused with these particular points, don't get confused with these particular points where it is shown that dw, when you are dealing with only a single parameter w, okay, so you can write dw. While you are taking the help of two parameters, say w and b, we need to, because we need to optimize two parameters w and b of the cost function j, see w and b. While you are using w and b, both the things, then you use this particular partial derivative. So it's quite funny. This is the representation. We use partial derivative while when j is a variable of a function of two variables, that is w and b, and while a single we can use only d and dp and dw. So this is how we update the value of w based on the points where we are on the slope. Okay, if it is a negative slope, we need to increase the value of w. This is where I shown how you need to increase, because negative slope means, again, this is dw is negative, so ultimately w equal to w plus something, so w should be increased if it is negative slope to reach this global optima, else it should be positive. Okay, okay, so any questions here? Because it's a very core engine we need to understand. Any questions I'll have to hear before proceeding to the next, how to compute the derivatives? Yeah.
Yes, sir. I'm unmuted. Sir, Dr. Srinivas Garu, you can
Yeah,
unmute.
yeah, sure.
Sir, is it global minima and global optima both are same or both are different, sir?
Little bit more. Can you please raise your voice a little bit? Your voice
Yes,
is
sir. Say here we start somewhere.
yeah.
I mean, randomly we pick up some values for
Yeah.
this W, and
Yeah.
it reaches to global optima.
True.
Or global minima. Is it optima or minima? Both are same or both are different?
No, same.
Both. Okay,
Yeah.
okay, sir.
Oh, thanks. Yeah. Anyone else, or yeah?
Sri Charan Garu is there. Just
Okay, Sri Charan. Yeah.
Sir, Sri Charan Garu.
Yeah, sure. Hi, Sri Charan.
Sri Charan Garu is not audible your voice.
Okay.
I'll give you another opportunity, sir.
Yeah.
Arjun Garu. Arjun Garu, you can speak.
Hello.
Yeah. Hi, Arjun.
Hi, sir. Good afternoon.
Good afternoon.
Sir, how can we check alpha, and is it constant throughout the any problem or not? How can we calculate the alpha? So, suppose you said you don't want to take more values, means higher value, but how much? What is the range to the alpha? How do we select for based on what is the criteria?
Yeah. See, this is again, I'll tell, this is an engineering science. So this is basically a trial and error. So you need to monitor the training progress and the accuracy curves along with the validation loss. So based on that, you need to select. So for example, if you have selected the value of alpha, which is big, and big in the sense, suppose we have selected 1. Okay.
Okay.
1, 2, 3. These are very big numbers. Generally, you select fractional numbers. Okay, so 0.01 is generically people use. So the thing is, if you use a particular value of alpha, which is very small, okay, the thing is, you can see from the graph, it will take a lot of time to reach to this global optima. Okay,
Yes.
and another way, if you take a very big number, so definitely from your intuition, you can tell that I can easily jump very quickly. I can traverse very quickly and I can reach the global optima. That is also
Okay.
true. But again, since it's a stochastic process, we never know that if you take a big jump, then it may happen that at this particular point, after taking a big jump, you may reach here. And then you may do like a pendulum. You may move like a pendulum from here again to here, again to here. So if you're taking a very big jump, okay,
Hmm.
I mean to say, to reduce that probability of taking a big jump and behave like a pendulum, like a to and fro. So people
Hmm.
take particular optimal values, I mean in between big and very small, so that there is less chance that once
Okay.
you are here, you may not jump to here again by taking a big jump. Okay, you may be
Okay.
very close to this. And the safest thing is you need to take a very small learning rate, so that there is very less chance that after here you may jump to here, you may come up to here. But again, that comes at the cost of very long training time. Okay, so there is
Hmm.
a trade-off. There is a trade-off.
Means we have to take a very small value for the learning rate. Means do you have any set of values, or shall we take as per our requirements?
Yeah,
Suppose
yeah,
if I
you
want,
can. Right, you
suppose
can
if I
take.
want to take 0.3,
Yeah,
is it okay?
0.3 is okay. Yeah, it's okay. But again, you need to. I should not say it's a very good number, because again, if you see the output curve, I mean the validation and this accuracy, how it is converges, the loss, how it converges. If it toggles a little bit more, then again you may need to retrain it by reducing the value of the learning rate to point 0 something instead of point 0.3. Okay,
Okay.
so that depends. That depends. Okay.
Okay. And could you please tell me that optimization point? How can we reach the optimization, and what is the value for that optimization? And what could you
Yeah,
please tell me
right,
that?
right. So this is, as I told, so this is a particular convex curve. Okay, and our target should be to reach this global optima. Okay,
Yeah.
so but the thing is, how we will reach this based on the value of how you update. I mean, because at every learning stage, you need to update the value of W. Now, how we will update based on the particular slope at present where you are. So suppose if you are at this particular slope, if you just consider the previous diagram, so 3D diagram. Okay, suppose you are at
Okay.
a particular value here. Okay, so uh, I'm assuming you are at particular value here. So this is a positive slope. This is a positive slope. Why positive? Because once you increase the W, your cost function also increases. Suppose you are at point here, and this particular point is the cost function, y-axis. And
Mm-hmm.
suppose if you increase W, definitely you can see the plot is here. So the cost increases. Okay.
Mm-hmm.
So that means on increasing W, if the cost increases, that means it's a positive slope. And here it is a negative slope at this particular point, because this, see, computing the derivative means finding the slope of this particular function at that particular point. Okay, of this function at this point. So it's drawing a tangent. So from this point, if you see,
Mm.
if we increase W, the value of J is decreasing. See, at this point, if you plot here, and again, if you go here, the value is decreasing of this y-axis is decreasing, right? So this is a negative slope and this is a positive slope. That means here, if you see in this particular function, if dw, that means djw, dw, you can write as only dw. This means this, okay? Djw by
Huh,
dw means
huh,
it is
huh.
dw. So if dw is negative, means you are at this particular point, say, okay, and you are moving right, W, you are
Mm-hmm.
moving right. Okay, so if the slope is negative, what happens? If the slope is negative, ultimately how W will be updated? W equal to W plus something, because this is minus and dW is also minus.
Minus plus. Okay.
Right, so it's plus. So
High
W
value will be increasing.
increasing. That means you have to go right. W, you have to increase the value. You are increasing the value of W. You are increasing. That means you are moving towards the global optimum.
Okay, sir. Okay. Thank you so much, sir. Thank you so much.
Similarly, here also, if you see, this is increasing. Here the slope is at this particular point, because there is no one to tell you. Suppose you are at this position, your neural network value W, the weights are here. Now, how you need to know?
Okay.
How will you know that you need to move left or right? Okay, you need to, because I know that you need to move left to reach the global minimum. Okay, but there is nobody to tell you that you need to go left. Okay, there is no guidance. So now how you will need to know? You will find the slope here. At this point, you find the slope here. This slope is positive because you know that this particular point, if I increase W, I am going to go up. I mean, the value of J will increase, and if I go left, the value of J will decrease. So this is a positive slope, because if I go right, the value of the slope will increase. Okay, it's a positive gradient.
Okay.
Positive slope. So that means if you are at this point, what will happen? How will you update W? That means W equal to W minus alpha of dW, where dW is positive. Okay, so if dW is positive, what happens? W equal to W minus alpha into a positive number. So ultimately, a W, how it will be updated? It will be decreased. Okay,
decrease the value.
Right. That means if W is decreased, that means you are going towards the global minimum.
Okay. Thank you so much, sir.
Okay,
Thank you so much.
Okay, so I'll move to the next slide. So here, yeah. Any other questions? I think. Okay. Okay, fine. So assuming it's okay. Okay, anyone raised his or her hand? Okay. So Jagan, I'm moving to the next slide or to
Sri Charan want to talk to you, sir.
Yeah, okay. Hi, Sri. Hi.
Sir, you can speak, yeah.
Yeah.
Sir, your voice is not audible. Sir, if you are facing any issue, you can chat. There is another option, chat box also.
Yeah. Okay. I'm going forward then. So here we'll learn a little bit basics about the derivatives. Maybe most of you after the graduate school we are not in touch with the derivatives, but anyway, so a little bit of brush up of our knowledge, and these core mathematical concepts are mandatory to learn to understand the gradient descent and how this backpropagation algorithm is functioning. Okay, as a core engine for this learning step. So the derivative is very important. So we'll see how we can reconsider or recall how we are doing the derivatives. Okay, it's just for the time being you forget about the formulas that you have learned. Okay, let's see how things goes on here. Suppose this is the x-axis, is the y-axis, and you know that finding a derivative means nothing. It's very simple, finding a slope of a function at a particular point. Okay, so here like a particular point 2 and its corresponding y value was 6, 2 to 6, and this function is fa equal to 3a. Okay, this is a and this is a fa. This is a, this is fa, and this function is 3a. Okay, so that means a, if it is 2, obviously fa is 6 from here. Okay, now let's see if we increase the value of 2 by a very small amount, that is 2 to 2.001. By scale, if you draw, okay, we may see that by increasing the value of 2 from 2 to 2.001, here we reach from 6 to 6.003. Okay, so similarly, so here I have written, see, a equal to 2, fa equal to 6, and if a is 2.001, fa is equal to 6.003. That's the point. As I told, for the time being, you forget about the formulas of derivative, and let's check, let's cross check, let's do the reverse engineering, and let's see how, what is the physical significance of this derivative is. Okay, now for example, here another point, say a equal to 5 instead of 2. Suppose I have taken a equal to 5. And then obviously from this function, f equal to 3a, we see f equal to 15 because 3 into 5 is 15. Okay. And say, let's check how the slope changes. Again, from 5, say, I have increased the value from 5 to 5.001. And by scale, we'll see that FA has increased from 15 to 15.003. So if you see from at both the cases, the increase, what is the increment? I mean, increase. So the slope is here, like increasing the y-axis by increasing the x-axis. This is the ratio we do, right? So here, if you see, in case of a equal to 2 and f equal to 6, so what is the change? That is 0.003 by 0.001. So that is 3. The change is 3, right? Here also the same thing, 15.003 by 5.001. So this is 0.003 by 0.001. So that is again 3. So that means the slope at a equal to 5 is also 3. So here, if from the line itself, from the function, you can easily understand the slope should have been constant, and here it is. Here also the increment is 3, here also the increment is 3. So the slope, like dfa by dA, is equal to 3. Now you cross check, now you recall the formula. What was that? Fa equal to 3a, and dfa by dA, what was it? It was 3. Okay, I didn't use any formula here. So from this scale measurement, we found out that the slope was 3. And then we cross checked from how did we derive that formula? dfa by dA, that is f dash a, is equal to 3. Okay, this is quite interesting to understand. Suppose here also, like one thing, suppose derivative here means we should increase a very small value. Here in scale, we I mean, it's easy to understand, we have incremented by 2.001, but it's actually not. We increment in this range, 0.00000001. In this range we increment generally, and then correspondingly we see how y-axis got incremented. Generally we don't increment by this big value, 0.001. In case of derivative, we increase by a very small amount here in this particular range. Okay, so this is something, one linear function, how we compute the derivative, how we, through the measurement, how we get it, and then we cross-checked whether it matches our formula or not. Okay, so here also the same thing. After completing this, I'll answer your doubts if any. So here, let us see with a nonlinear function here. So say, for example, fa equal to a square. So here we'll see in nonlinear case, at every point the value of the derivative, the value of the slope will vary. Okay, that's the reason why it's a nonlinear curve. Okay, so it's a polynomial anyway. So fa equal to a square. That means here, for example, I am checking at a equal to 2, the function was 4. I'm checking here, it's 2 at 4. Okay, now at 2.001, suppose I've incremented a little bit, 2.001, and I will see that the function through scale, we'll see that its value is 4.004. Okay, so there can be a little bit more increment also, but we can discard this. So approximately it is 4.004. That means if you see the derivative of the slope of fa at a equal to 2 is 4. Why? Because see, this is 2.001. Once increasing, I am increasing 2 to 2.001, and correspondingly 4 has increased by 4.004. Okay, so 4.0, that is 0.004 by 0.001 is actually equal to 4. So the derivative at the slope of the function at point a equal to 2 is 4. Okay, now another example, say at a equal to 5. For example, I'm changing the point a equal to 5, and fa is 25 because the function is fa equal to a square. So at a equal to 5, fa is 25. And if I increase a by 5, from 5 to 5.001, it becomes 25, like 25.010. Okay, from 25 to 25.010. So then what is the slope? That 0.010 by 0.001, that is, it comes to like 10. Like 0.010 by 0.001, that is 10 when a equal to 5. That is, the slope at a equal to 5 is 10. Initially we saw the slope at a equal to 2 was 4. So that means the slope is not constant. See, it is varying from 4 to 10 in this way. Okay, so similarly, if you check now, cross check, do the reverse engineering and see what is dfa of dA, because dfa was a square. So d of a square by dA is actually 2a. Okay, now you cross check. That is when a equal to 2, the derivative was 4. 2 into 2, that is 4. Derivative was 4. And here, like when it was 5, I mean, yeah, when the a is 5, so 2 into 5, that is 10. That is dfa by dA equal to 10. So it matched. Okay, so that is physically we are measuring, and then we are finding the function, I mean the gradient, the slope, which is nothing but the increase in the y by the increase in the base. Okay, perpendicular by base, and that is what is nothing but the slope of this curve at this particular point, and that is what the derivative is. So now you try to find a relation, like derivative is nothing but nothing like finding a formula. So it's basically a physical representation of what is happening here on a scalar view, on a taking a pen and a pencil, and paper and pen and a paper, and taking a ruler, and if you compute here, this is what the formula comes. This is nothing magic. Okay, I hope you enjoyed this. Anyway, okay, so I'll just compute one more example here before going to the this is computational graph. Okay, so one more example here is quite interesting. If you see, if a is a square and if a is a cube, similarly that we know the formula, like if a square means 2a and a cube means 3a square. So here again you can cross check in the similar way, like if a equal to 2, if a is 4, if you increase by 2.001, it will be increment by this amount. A square you already saw. Now let's see the example of a cube. So if you see a cube, like it is how it comes to 3a square. Suppose you check here, we can just do it on your own, that a is 2, then fa is particular this value, for example, approximately. Now if you increment a by 2.001, this value becomes this. Okay, then you divide this. How is this increment happening? Then you will get that the increment is like this AQC. Say, suppose this particular value, a equal to 2 and fa is 8. I'm taking this example, a equal to 2 and fa is 8. So if I increase 2 by 2.001, 8 will be incremented approximately by 8.012. Okay, through scale, if you map, you will be able to see. So that means how it is increasing. See, so what is the increment? That is, if a equal to 2, fa is 8, and if a increment a by 2.001, fa will be 8.012. That is this x-axis. If I increment a, and y-axis fa will be increment by this value. So what is the difference? I mean the ratio, that is 0.012 by 0.001, that is 12. That means 12. So if you do dfa of dA, it becomes 3a square. Okay, now put a equal to 2 here. What it will become? A equal to 2. If I put a equal to 2 here, that is 2 squared is 4. 4 into 3 is 12. Okay, so that matched with this previous one. In the similar way, if we see another example of a log, okay, so if a equal to log base e of a or ln a, whatever you call, is a logarithmic curve, and we already know. Just for the time you forget about it and you check, we already know of the derivative of this log is 1 by a. This we already know. Okay, so we'll cross check how it becomes 1 by a. So suppose we are taking, if a, this a, and this is a particular value. Okay, if a is 2, then fa is this number, log of a, and if I increment a by 2.001, the value will be this. Okay, so that means what is the change here? If I increment by 0.001, what is the change? If we see, this is the change. If we subtract this, we'll check, that is 0.69365 minus 0.69315. So it becomes 0.0005. So with this increment, we got a change in the y-axis, this increment. So if we divide this, you can use a calculator, a pen and paper, you can use that 0.0005 by 0.001, it will be half. And that matched with the original formula. Okay, so this is what about the physical realization of what is the derivative is nothing but the slope of computing the slope of a particular function, okay, at any particular given point. And that's what the derivative is. So we checked with the formula, we checked how the formula is matching with the if we use a ruler and a pen and a paper and we measure through a scale and if we check it. So that's the thing. So next we will talk about the computational graph and how to use that to compute the derivatives or more complex functions. In the next slide we'll see. Okay, so before going into the next slide, I'd like to uh, uh, answer your queries if any. Yeah, hi Jagan, any questions?
Yes, sir. We Sri Chaitanya has raised the.
Yeah, okay.
Sir, you can. I can speak.
Sir, this is Sri Charan, sir.
Hi Sri, how are you? Yeah.
Yeah, fine. Thank you, sir. Sir, can we define the termination condition for gradient descent?
Terminating condition, yeah. So the terminating condition that you have to decide how you, I mean, based on your monitoring process, you need to monitor the training procedure through the so at the end of this class we'll show a few programs. We'll show a few programs, and also it will be more prominent tomorrow also. While we do the programs, we'll be seeing the monitoring the loss curve, and we'll be monitoring the accuracy curve. So there we will see the accuracy after certain epochs, after certain iterations in the training will reach the saturation stage. Okay, so there at that particular point of time you can stop your training process. So that will define that the training is over. That means your gradient descent, through your gradient descent you have reached the global optima. So that is what, through the monitoring process we have to find that particular point.
Okay, sir. Thank you, sir.
Thanks. Yeah.
Sir, we have one more.
Yeah, sure.
So here I'm Srinivasa Garu. I am muted. You can.
Sir. Good afternoon, sir.
Yeah, hi, good afternoon. Yeah,
The nice way of explanation. Thank you, sir.
thank you. Thanks.
Sir, may I know the last one, dfa by dA equals to 1 by A.
Yes.
Then we got 1 by 2.
Yes.
Then how we can correlate this one with this particular graph? How we can find the slope for this one, sir?
Yeah. See, the thing is, this is the formula. DFA by DA is 1 by A. Now, how you got this? How you are getting half? Okay, that means 1 by A means A, if A is 2, so 1 by 2 is half. So here, if you plot this, like A at A equal to 2 log of A, you are getting this particular function. You are getting FA is 0.69315 at A equal to 2 based on this curve. On this curve. Now, when you increase 2 by 2.001, okay, you will see that FA is approximately equal to this, because see the value is increasing, little bit increasing. Okay, little bit increasing from this curve. If you see the laser pointer here is increasing. So that means at 2.001, once you increase here from 2 to 2.001, this particular point, you will see the function of FA moved from 0.69315 to 0.69365. So what is the increase in this function? That means this is the increase. Okay, if you subtract 0.69365 and 0.69315, this is 0.005. So then you need to, this is the ratio, 0.0005 by 0.001.
That will be the slope.
Yeah.
Good. Thank you, sir. Sir, if possible, kindly include how to define a function such a way that the gradient should be minimized. If possible, sir. It's my request.
Okay. One more time, please. Which one you are asking to include?
Define a function such that the gradient should be minimized.
Okay, a particular function where the gradient is okay. Gradient is minimized.
Yes. Like that.
Okay. Yeah. So for example, if you see.
No, sir.
Okay.
Possible that no problem.
Okay. Fine. Sure.
Thank you, sir. Thanks.
Okay. Thanks. Okay. So you see the underlying skeletal structure of a neural net through the use of the computational graph. Okay. Suppose how the signal flow happens within a particular neural net. This is what is shown through a computational graph. So whatever you do is basically a computational graph in neural networks. Okay. So the thing is, here is a formula. If you see, J A comma B comma C is equal to 3A plus BC is equal to 3 into 5 plus 3 into 2 equal 33. How you are getting this? Okay. Just a point. Was recording. Yeah. Okay. So so what we saw here is called a computational graph. Okay. Am audible, Jagan? I'm audible.
Yes, sir.
Okay. Okay. So if you see here, that is 3 into A plus B into C. Okay. So here, if you see this computational graph, that is we are terming B into C as U. V is equal to A plus U. That is this entire term is V. Okay. Let me use this laser pointer. So V is basically A plus U, because already I told B into C is U. So V is A plus U, and J is 3 into entire thing, that is 3 into V, because V is this entire thing. Okay, so U equal to B into C, V equal to A plus U, J equal to 3 into V. So with this, let us assume that A equal to 5, B equal to 3, and C equal to 2. Okay, that means B into C, that is U equal to B into C is 6 here, and V is A plus U, that is A is 5, 5 plus U, that is 5 plus 6, that is 11 here, and J is 3 into V, that is V is here 11. Okay, V is 11 because V equal to A plus U. A is 5 and U is 6. 5 plus 6 is 11, and J equal to 3 into V, that is 3 into 11, that is 33. So this is what a computational graph is. Now let's see how we find the derivatives with a computational graph. Then we'll see the back propagation. It's very interesting. Just a point. Just a moment. Okay, so here the thing is, similarly, if you compute here, like we need to find dj by dv. Okay, so how you compute dj by dv? If you see here, like the b equal to 3, you increase, like it's like a chain rule in calculus. It's called a chain rule in calculus. So if you change b from 3 to 3.001, what will happen? Suppose these are the initial values. Okay, hello, Jagan, am I audible? Yeah, hello, Jagan.
Sir, your voice is audible.
Yeah, okay, okay. So suppose here, if I increase b from 3 to 3.001, what will happen? We know u is equal to b into c. That is, b is 3.001 into c is 3. C here is 2. So 3.001 into 2. Okay, that comes to 6.002. Okay, that means we, with change in b from 3 to 3.001, we get a change in u 6.002. That is, we change in b made a change in u. Is a chain reaction. Similarly, a change in u will make a change in v. How? See, so v, what will happen to v? V we know a plus u. So initially it was 11, right? Because 5 plus 6, 11. A was 5. Now it is 5 plus u will be 6.002, right? So 5 plus 6.002, that is 11.002. So you can see now a change in b had resulted in a change in u, and that in turn resulted in a change in v. And so if we change v, again j will also vary, because j initially it was 33, now it will be 3 into, what is v? 3 into 11.002. Okay, so 3 into 11.002, so that is, you can easily compute and you can see it will be resulting in a change in j. Okay, so finally what we get is, so if you need to compute what is dj by dv, okay, dj by dv, So dj by dv means what is the change in v? I mean, what is the change in j here with the change in v? That is nothing but dj by dv. What is the reflect? What is the change in j we see once we change v? Okay, so that means we know if we change v by 11 to 11.001, we'll see a change in j, that is 33 to 33.003, because j is equal to 3 into v, that is 3 into 11.001, that is 33. So basically dj by dv is 0.003 by 0.001, that is 3. Okay, you can easily cross check dj by dv is equal to 3 with the differential calculus formula. Okay, the similar thing we had seen here with this derivative. That's the reason why we spent a couple of slides during this in that derivative part. Okay, to make you understand here. Okay, so now similarly, if we see here a, if we change a, suppose here a to 5 to 5.001. Okay, so if I change a 5 to 5.001, what will happen to v? We know that v is equal to a plus u, that is 5.001 plus 6. Okay, so that is 11.001. And similarly j is from 33, it will become 33.003 because j is 3v. Okay, so here if you see dv by da, what is dv by da? That is what is the change in v if we change a. Okay, what dv by da, what is the change in v if we change a? So we saw that if we change a by from 5 to 5.001, v also changes an equal amount, 11.001. Therefore dv by da is 0.001 by 0.001, that is 1. Okay, so this is dv by da. Similarly, if I ask you, you find dj by da, that is dj by da. What is that? Through a chain rule, we know dj by da is equal to dj by dv into dv by da. Okay, by this thing we are trying to introduce you to the back propagation through this derivative. Okay, that you have to understand. So that is what are the changes in weights that we need to do in order to reflect in the output state. Okay, so that means dj by da, again, and remember, just recall dj by da. What is dj by da? dj by da is actually dj by dv into dv by da. So this is a chain. That means with change in a, there is a change in v, which result in a change in j. So dj by da is dj by dv into dv by da. We already know dj by dv is 3 from here. dj by dv is 3, and dv by da is a constant 1. So 3 into 1, that is 3. That is dj by da is basically 3. So in this way we compute the derivative. We saw with the formula as well as by the change, how it is changing. Now suppose if you ask me how to compute dj by db, similar way, dj by db, how b is related to j, that is b is related to u is related to v is related to j. In the previous case we saw how a is related to j, a is related directly to v and v is related directly to j. So here b is related directly to u to v to j. So that means dj by db, see here, dj by db is basically dj by dv, dv by du, and du by db. See, dj by dv, dv by du by db. So we already know dj by dv, from here it is 3. dv by du, we know this is 1. dv, okay, sorry, dv by du. Okay, so yeah, let's check what is dv by du. That is what is the change in v if you change u. So that means suppose I'm changing u from 6 to 6.002. Okay, so that means v is a plus u, so a is 5 and u is 6.002. So that is 5 plus 6.002 is 11.002. That means if I change u by 0.002, v is also again changing by 0.002. That is dv by du is 1. So here just you put du by dv by du is 1, and du by db we already saw. Du by db it is du by db it is 2. Okay, so that's the thing. So finally you see dj by db is equal to dj by db is equal to dj by dv, dv by du, and du by db. Okay, that is 3 into 1 into 2, that is 6. In a similar way, this is an assignment, you can try dj by dc. Okay, so this is how we find the derivatives with the computational graph. Okay, so finally what happens is a to v to j, b to c to u v to j, c to u to v to j. In this way we can compute. And finally we have to find always mean that the d final variable by dv is okay. So like if you are finding say I mean d of this final variable j, dj by dv means you are finding dv basically. So suppose you are finding dj by dA means you are finding dA. Okay, if I write like only dc, db or dA, that means it is with respect to the final variable. That is dj by dc, dj by db or dj by dA. If I write dj by dv, that means I can only write dv. That means it means that dv, that is what is the change in v which has resulted in a final output effect. What is the change in, if I write dj by du, okay, that means it is only du. That is what is the change in u which has finally affected dj. So in this way you remember. Okay, this is a conventional way of representation, and this is how we do the derivatives with a computational graph. Okay, so any questions in the previous slide? Yeah, okay. Yeah, any questions I would love to answer? Hi Jagan, so will I go ahead?
Hello.
Yeah, hello. Any questions from the previous slide?
Sir, one person want to use it is Karmala. Can I connect to user?
I'm not being able to hear you. Can you take your microphone a little bit close? Yeah, hello.
Hello.
Yeah, hello. Yeah, tell me.
Sir, one person want to go talk to you. Should I go ahead?
Yeah,
Should
please.
Good afternoon, sir.
Yeah, hi, good afternoon.
Sir, is it mandatory to first derive the these derivations and then go for the computational graph?
See, computational graph is already present. Okay, so whatever I'm explaining is it falls under the backpropagation algorithm. So whatever you need to do to implement the backpropagation algorithm is you need to compute the derivatives, because you need to realize the gradient descent. Okay, so the gradient descent is basically computing these internally these derivatives with the respective variables and the nodes in the computational graph to implement the backpropagation algorithm so as to update the weights and finally getting converged to the pretend model. Okay, so
Okay,
this
sir.
is what is internally is happening. Okay, just why I'm explaining, just because so that you can understand the engine behind this.
Okay, sir. Okay, thank you, sir.
Okay. Okay, so if I continue next, like this is the logistic regression with the gradient descent. Okay, anyone else, please? Yeah.
Sir, Karimula want to talk.
Okay, yeah, hi.
Hello, hi sir.
Hi.
Sir, will you go to the previous slide one, sir?
Yeah.
Actually, I understood like that will be calculated with the help of the slope, like height by width.
Yeah,
Uh,
yeah.
Here, how we got like 0.02 by 0.002, sir? Derivative of v by derivative of u. What is the uh,
Mm-hmm.
from where the digit came? I didn't understood, sir. And
Mm-hmm.
coming to the fourth line also, dj by dv equals to 3. From where it is? From where we got the dj by dv equals to 3?
Mm-hmm. Okay, okay. I'll come one by one to your questions. Yeah. So you mean to say how you got this? See, if you see this computational graph, so this every formula like this is u plus v. So that is j is equal to 3 into v, and what is v? V is a plus u. Okay, and what is u?
Yes, sir.
U
That one I
equal to b into
understood.
c. So here, how you are getting dv by du? Actually, dv by du means what is the change in v if you
Mm.
change u, right? What is the change in v if you change u? This is clear to you? Hello?
Sir.
Yeah. So the thing is, what is the change in v if you change in u? So the u, what you are changing, u is actually 6. U was actually 6. So if you are changing u by from 6 to 6.002, okay, so 6.002, if you change u, then how it is reflected in v, because v is a plus u. Okay, so a is 5 and u is 6.002. So 5 plus 6.002 gives 11.002. That is, you made a change in u by 0.002. That is, you made it from 6 to 6.002. So v, originally it was 11, now it is 11.002. So what is the change in V that happened? It's actually 0.002, because it changed from 11.002 to 11 to 11.002. So the change dV is 0.002, and what change you have made in U is 0.002. So 0.002 by 0.002 is equal to 1. So dV by du is equal to 1. Does that answer your questions?
Um, Please respond in the chat box, or you can change. You could raise the hand. Yeah, it's clear, sir.
Okay, okay. Thanks. Okay, similarly, the second question that you asked is dj by dB, how it becomes. As I told, is a chain rule. dj by dB, that is with a change in b, how it is reflecting in the change in j. So you see directly there is no link. There is a link through u, v and j. That is, if you change in b, it will result in a change in u, because u is equal to b into c. And if you change in, there is a change in u, it will be reflected in a change in v, because v is equal to a plus u. And finally, if there is a change in v, it will be reflected in the change in j, because j is equal to 3 into v. That means dj by dB is basically dj by dv, dv by du, and du by dv. So this is how it is linked. And individually we know. So that is dj by dv is 3, dv by du is 1, du by db is 2. So 3 into 1 into 2, that is 6. So dj by db is 6. So is it clear?
Yeah, we got a response in chat box, sir. It's clear.
Okay. So Jagan, I think one of the previous videos yesterday's.
Yes, sir.
Do we need to delete? Otherwise, as he's saying, it's like the chat. I mean, the space is a crunch.
We can delete, sir. We have already. I downloaded. I hope you are already. You
Yeah, I
have a
already
backup.
downloaded. So can you delete one of them? Otherwise, this particular ongoing video may get hampered.
Yeah, I'll delete it, sir.
Okay.
Yeah, thank you.
Okay. So it is on 15th. Yesterday is one of the videos.
Yeah, yesterday videos.
Okay. Okay, so I hope this particular thing is clear. With this, we'll move on to the logistic regression that we saw. So it's just a recall. There, how we are going to apply the gradient descent. Okay, fine. So just the recalling logistic regression. If you recall all these formulas, I won't repeat here due to shortage of time. So Z was WTX plus B, Y cap was sigma of z, and this was the loss function. So just assuming w1 x1 w2 x2b are the parameters, we can write in this particular way. See w1 x1 plus w2 x2 plus b. Okay, so that is basically z. So this you can think as wx plus b. We are using just extra parameters. Okay, so wx plus b. So in this way, w1 x1 plus w2 x2 plus b, which is z, and y cap is the activation, which is sigma of z, and finally we get the loss. Loss a is the predicted output, that is y hat, and y is the ground truth. So this difference is the loss. Okay, so now the thing is, with your calculus knowledge, if you just try to do this derivative on your own, just practice it out, you will get that dl dz basically. So dl dz is dl dA into dA dz. Okay, with this particular notation. Okay, if you think like w1 x1 w2 x2, one second, yeah, w1 x1 w2 x2 plus b, this is basically z, and which resulted in, after z we find sigma of z, that is a, then finally loss. So if you find dl by dz initially, dl by dz, this is which is basically dl by dA into dA by dz, because a is the in the middle of the path. Okay, so you have to find through a, that is you have to find, if you want to know what is the change in the L with respect to z, we have to find dl by dA, dA to dz. Just recall initially what is the chain rule of this differentiation calculus. So we know that dl dA, if you find dl dA, because L is the loss function, this particular loss function, if you do a derivative with respect to a, you will get this. Try it out at your home and your free time, and you'll get more interest. So dl dA is basically so dl dA is basically minus y by a plus 1 minus y by 1 minus a. If you do a derivative with respect to this particular function, you will get this. And dA dz is basically a into 1 minus a. Okay, if you do dA dz, because what is a is basically sigma of z, and sigma of z means 1 by 1 minus e to the power 1 by 1 plus e to the power minus x. Yesterday we saw that formula, 1 by 1 plus e to the power minus x. Okay, so you will do dA dz, you will get a into 1 minus a. So that means if you do dl dz is equal to dl dA into dA dz. So you just multiply these two things, dl dA into dA dz. Upon multiplication, we will get dl dz is a minus y. Okay, dl dz is a minus y. Similarly, we can also find the final loss with respect to initial w1 as a parameter. We have checked with z, now we can check with w1 x1, all these things. Okay, so dl w1, similarly, if you try to find dl by dw1, what is it? We have to find dl by dA into dA by dz into dz by dw1. Okay, so this is the chain rule. Hope you can understand how it is linked. Just think initially w1 x1 w2 x2 forms this z. Okay, so how they are combined, w1 x1 plus w2 x2 plus b forms z. Then once we have z, we need to find sigma of z, that is the activation. Okay, once this is found, then once this activation, the output of the activation, that is a y cap predicted, is found, then we are in a position to find the loss of y cap or loss of a comma y. So that means if you want to find dl by dw1, the initial value dl by dw1, you need to do this chain rule. Just try to recall from this initial computational graph how we went back. So dl dw1 is dl dA into dA dz into dz dw1. Initially these three need to compute, so we'll get something like this. Okay, a minus y, because we already know that dl dz, okay, dl dA into dA dz, that is dl dz is a minus y into dz dw1. Okay, so dz dw1 is basically x1. If you compute, it will come, it's basically x1. Okay, so that means dl dz into x1, we can because a minus y is basically dl dz into x1. So finally we can write dl dz at dz. So x1 into dz we can finally write. So dl dw1 is basically x1 dz. That means dl dw1, I know I told you that dl dw1 means you can only represent this as dw1. So dw1 basically finally converges to dw1 is equal to x1 into dz. See, dw1 is equal to x1 into dz. Similarly, dw2 will be x2 into dz and db equal to dz. So what do you mean by db? It is actually dl by db, and dz means dl by dz. So once you get dw1, dw2 and db, you can now finally upgrade the value of the weights of the neural nets in this way, as I shown in the previous slides. That is w1 equal to w1 minus learning rate alpha of dw1. Once you have found dw1, then only you will be in a position to compute this and upgrade the value of w1, w2 and b as the parameters. So b is equal to b minus alpha of db. It will be actually db. Sorry, there's a small printing mistake here. It will be db. It will be db. B equal to b minus alpha of db. So in this way you back propagate. You have seen in this way you back propagate through the computation of these derivatives and finally get the change in the weights, which you update, and this goes on this iterative step. So this is like a logistic regression derivatives. Okay, now we are going to see how this is applicable on M examples. The previous thing we saw for a single example. Now we will see how we apply this for multiple examples. How this is applied for multiple examples, M examples. Okay, this is very interesting. So because the previous parameters, that is true for while you are applying this on a single example. Now how the representation looks like will be looking like when you are applying this to multiple examples, M examples, say. Okay, so every other thing remaining same. Just try to understand every other thing. Recall from the formulas. Every other thing will be same. This is a cost function, activation, ji, because this I superscript I means I is equal to 1 to m. Okay, when I write only I means a single training example. When I am writing I mean this individual ith value means a single training example, but actually I is running from 1 to m. I'm considering for all the training examples. Okay, so here it is like you need to run a for loop. Okay, for I equal to 1 to m, for j equal to I, this is the thing wtxi plus b, and ai the activation is sigma of j I. This is, and this then after finding this we basically update the value of this cost function. Okay, there is j of wb, if you remember. After finding this with the complete package, we need to update the cost function by computing individual losses, and then we update the value of w1 and w2 with these formulas that we have already computed in the previous slide. Okay, finally what we do is we divide it by the average of m. Okay, dw1 by equal to m means dw1 equal to dw1 by m. Okay, so this is how we do the logistic regression on m examples for I equal to 1 to m, and this I is running from 1 to m. This is using a for loop. However, there is one problem here is using a for loop. I mean, it definitely reduce. I mean, it makes a lot of delay. Okay, you need to iterate all the individual training samples. Instead of that, if you want to try to leverage the power of your multi-core architecture in your either in your CPU, if you are using CPU or GPU, then also you can use that through a process called vectorization. Okay, because we will see a particular program next that if you run this vectorization on without vectorization and with vectorization, you will see the timing difference of the training. Okay, so obviously you need to iterate through all the training samples, but with the use of the single instruction multiple data type of architecture, you can utilize the multiple cores, the multiple threads that are running on the individual cores of the CPU or the GPU, and you can do an extreme parallelism there. Okay, so we'll see the next slide what is the vectorization.
Sir, we have an interrupt. Small. Ram Garu want to have a question.
Yeah, sure. Yeah.
Excuse me, sir.
Yeah. Hi.
See, in the last when you go back to past two slides,
Okay.
so we have calculated the value 6.
Yeah, this one you mean to say
Yeah,
6?
6.
Okay.
No, yes, sir, this one.
Okay.
We have calculated 6. 3 into 1 into 2 equal to 6. What does mean this 6 means? Yeah.
Okay, this 6. Okay, this 6 is actually dj by db. That is what
Yeah,
is
dj by db. Sir, when we
Mhm.
calculate, because of this formula, we calculated this is 3, this is 1, 2. So what this 6 actually represents, if I change a little bit of 0.001, is it 6 units of j value is change, or what does mean actually?
Yeah, that's what I told you. Now, as of now, just forget about this formula. Okay, this dj dv dv du du db, forget about this.
Okay.
Just look into this particular picture.
Yes, okay.
Okay, so if you change b,
Okay.
okay, if you change b from 3 to 3.001,
Okay.
just compute from here, assuming you know a and c.
Oh.
If you change b, then how j will be reflected? What is the change in j that you will see? That is what.
Okay, sir. One more thing, sir, in the next slide.
Yeah. So did you got my answer here? Any doubt?
I got it, sir. I got it,
Okay.
sir.
Okay. Yeah.
Sir, here we have calculated dl by dz.
dl by dz. Yeah.
We have calculated dl by dz. That means we are differentiating this loss equation with respect to z.
Yes.
So z includes already w parameter, x parameter.
Yes.
Why should I do again with respect to w1, w2, and all those things?
No, see, they are assuming these are the parameters w1, x1, w2, x2. Actually, parameters here are w1, w2, the x1, x2, and b. These are the parameters.
Yes, sir.
Okay. So, and z and these parameters constitute z. Okay. So, basically, if you want to find the value of the change in this loss with respect to any of these parameters, say it is w1, x1, w2, or x2, or even if you want to find, because if you are finding dl by dz, okay, ultimately what is the change in z that is reflecting in the loss, and change in z means ultimately you are reflecting the change. I mean, if there is a change in w1 either, or if there is a change in either of any one of the parameters, then it will be resulting in a change in z. Okay, and if there is a change in z, definitely a will be changed because a is sigma of z. Okay, and if a changes, then obviously L will also change because L is actually parameter of a and y.
So y is the actual value and a is the calculated value. Yes, sir.
A is the predicted value, right? A is y cap.
A is the predicted value. Y is the actual value.
Right.
Using logistic regression, we are having a formula. So
yes, this is the loss.
We are derivating the formula minus y by a plus.
Yes, absolutely. See, that's why when you are doing dl by da, okay, dl by da means d of this complete thing minus y log a plus 1 minus y log 1 minus a. This is completely L. So dl by da means d of this by da.
dl of.
That's the reason why you are getting this. So this you can, with a pen and paper, you can just compute the derivative. So dl by da means d of this entire thing by da. Then you get this particular expression.
Sir, actually L is composed with two values a comma y, sir.
Yes.
So when we do dl by dz, so how we can split dl by dz as dl by da into da by dz. So a itself is that actual calculated value.
Yes.
A itself is the actual calculated value.
Right. Now see, dl by dz is actually dl by da into da by dz. How? Because if there is a change in z, see how the chain reaction, if there is a change in z, okay, if there is a change in z, that will affect a, because a is sigma of z.
Okay, sir. Okay.
Is it okay? If there is a change in z, definitely there will be a change in a, because A is sigma of Z.
Okay, the sigma.
And what is sigma of Z? 1 by 1 plus e to the power minus Z. That formula you know.
Okay, sir. So capital L changes with respect to A, whereas A changes with respect to Z.
Absolutely, 100% correct.
Yeah. Okay.
Okay, that's
Sir,
what the chain rule is. Yeah.
These are the mathematical calculations, sir, that I understand.
Yes.
Please go to the next slide, sir.
Yeah, sure.
Sir, here in the for loop, by calculating for every input, we are updating keep on weights.
Yes, true.
So not for after calculating the entire error, we are not changing the weights. Incrementally, we are changing the weights. Is here?
Actually, yeah. Can you repeat once again? Like this is for
Sir,
I equal to 1 to m. Yeah. For all the training samples. Yes.
See here, the weights are updating for every input. When you supply X1, the weights are updated with D1, DW1, DW2.
Yes.
Sir, here, first input X1 we are giving based on the error is calculated, and based on that DZ is also calculated.
Yeah.
Immediately we are updating not actual value, some temporary variable DW1, DW2, DB. These are the temporary variables.
Yes.
Finally, the averages of these complete differential values we are updating with.
Yes. So I'll explain this in the next subsequent slides. It will be coming how you pass each and every training examples and how you vectorize the entire thing. Okay, how you stack the values of W, how you stack the values of Z, and how you encounter this, because this is for all the training samples, and all the training samples are passing through all the parameters of the neural net. Okay, how the representation is, it will be more clear when I come to the next slides.
So this DW1 is the difference between with respect how much you want to change with
respect to
W1
L.
per value.
Yes, because DW1 is actually DL by DW1.
Yes, sir, DL by DW.
Yes.
So we are calculating, we are not updating weight once. Weight values, we are not updating the for loop. Is it right, sir?
Yeah. We are updating. Yeah.
We are updating or we are not updating?
So here we are updating. Yeah, we are updating.
The weight values, sir, initially we have started with some weight values, sir.
Yes.
These values are updating, keep on for every input?
Yes, absolutely. Yeah.
Okay.
That's the reason why I have put there I. See, in the superscript, it is written I.
Okay.
Okay, that means dw1 plus equal to x superscript x1 superscript I dz superscript I. Okay, that means for every value of I, this dw1 is getting updated. dw2 as well as db.
Okay, sir.
So here I have shown for every samples how you need to iterate through the help of a for loop. But the thing is, this explicit use of this for loop should be avoided. Okay, and how you need to avoid? So Python has got some inbuilt libraries. We'll see that NumPy library, with the help of which it basically explores or exploits the SIMD instruction of the processor instruction set of the processor of our multi-core architecture. So there's a process called vectorization. We'll see next how we can efficiently utilize the multiple cores of our system.
Okay, sir.
Okay.
Thank you, sir. Thank you.
Okay, thanks. Okay, so once we use a for loop, that's a non-vectorized representation. That should not be. We should be able to use a vectorized implementation. Okay, so if you see here the representation in the left hand side, Z is equal to WTX plus B, the non-vectorized, that is initializing Z with 0, then for I in range n minus x. Okay, it's basically a Python we have Python script that we are writing. Z plus equal to WIXI. That is for every I. I is ranging from 1 to n minus x. Okay, and z plus equal to b, we are updating. So this is the use of a for loop. This is a non-vectorized. Now how we can represent this with the help of a vectorized implementation? So as you know, w, it can be represented as a column vector. Similarly, x can also be represented as a common column vector. Okay. So if I use the function np, so we will see one code in the next slide. This we will implement. Once we have z is equal to np numpy, import np as numpy, we will write import np as numpy. Sorry, import numpy as np. Yeah. So np dot, use the dot product here, w comma x plus b. So this numpy array, this library basically will implement this dot product of w and x. It will take hold of this particular vector in this column vector w and x, and it will one to one, it will multiply. And finally, the value of z will be upgraded to z equal to z plus b. So it will do this with the help of this SIMD instruction set of the processor. Whatever you are using, if it is a GPU or a CPU. Obviously, GPU, if you use GPU, it will you get a more effective implementation because multiple cores are number of cores are dedicatedly the cores are CUDA cores are more in GPU with respect to the CPU, and a very small homogeneous set of cores are present in the GPU that will accelerate much more. But anyway, with the CPU also, you can see the difference of a vectorized and a non-vectorized implementation. So that I'll just hand it over to I think Jagan. Hello.
Sure.
Jagan, this code I'll just transfer the screen in your Jupyter notebook.
Okay.
So can you just execute and show the audience?
Fine, sir.
So Jagan, I'm sending. Jagan, I've sent you. Yeah, hi Jagan.
Yes, sir.
Yeah, I have sent you the entire code.
Yes, sir. Just there.
Yeah.
Now
So,
I hope it is visible.
right. So initially, just we can print A and just show, and then you can run that from import time onwards. That's a separate program. Yeah, yeah. This is a separate program. Yeah, yeah. I hope everyone can see the screen of Jagan.
Yes. Okay. Just I'm running the fast shell. You can see the fast cell input, sir.
Yeah, 1, 2, 3. Just print 1, 2, 3, 4. So Jagan, you have is resumed the recording, right? Yeah, it's recording.
Recording, sir.
So the output from the second one we will get.
Let me run the second one, sir.
Yeah. Run the second one, please. Yeah.
It's a copy in the chat box. No, it's.
Oh, okay. I see. Yeah.
It's a different format.
Yeah. Oh, I think yeah. Here also.
If anyone copied the code, just check it. The syntax is some getting somewhere in the syntax error. Yes, sir. We need to keep a colon for loop. It's inside the loop, sir.
Yeah.
Yeah. Fine. So it's showing C is not defined, but C is there.
Okay. Is not defined.
I think here.
Okay.
Sir, we're getting out of the box error.
Yeah, I think that is instead of 1000 in that range you need to decrease.
Yeah. Let me create an array object.
No. I think I in range that particular 13 line number 13.
I range. Let me reduce.
Yeah. You can make it 1000. Yeah, you can make it 1000. Yeah.
Yes.
Yeah. Okay, so you can see the vectorized implementation, vectorized version. What is the total time? And for non-vectorized, what is the total time? $242. So almost like 243 times faster. Okay, so Jagan.
Sure.
Yeah, you can tell them. I can tell that what is the difference. Like the vectorized version is what is the time taken 0.9942 millisecond, and here it is taking 242.
This is the one, sir. Second time.
Yeah. So the vectorized version. What is the time taken? It is. Okay, I think you need to rerun it once again.
This is the vectorization, sir.
Yes, yes.
It's a 0.
Okay, can
And
you?
this is a for loop.
Yeah. So next one, there is 260. Okay, 260.
It's a 1.9 milliseconds.
And the previous one was point. Yeah. So you can find the difference, right? Hello. Yeah. Jagan, can you run it once again?
Yes. Run once again, sir.
Yeah, yeah.
Now
Can you
it is
run?
it is showing 1.9.
Yeah, yeah, yeah.
0.
Yeah, yeah. So it is for only 1,000. 1,000 iterations for 1,000 random numbers. Okay. So if you increase the numbers from 1,000 to 10,000 to 1 million, you can find a huge change in the difference.
Index error.
No, it will be 1,000. Because we have initially selected 1,000, no? Random dot rand 1,000. This is 1,000. So this should also be 1,000. So if you increase from 1,000 to 10,000, you can just check. 10,000.
Let me increase, sir.
Yeah, yeah, yeah. Just 10,000. No more, not more than that. 10,000. Yeah, here also 10,000. The range you increase by 10,000. Yeah, now you run it. Okay, hi, Jagan.
Yes, sir. Now in the vectorization, it's showing a 442.
Yeah, and in the below.
And for loop, it's a 9 milliseconds.
No, I think this 2526. This is the correct one. 2526. Yeah. This is the print.
We need to increase, multiply the here 1,000 also. Here also.
No. That is the millisecond. That is millisecond. Yeah, this is millisecond actually. So it is printing C. 1 point it is printing C here. Jagan, this print C. Can you just put on hold? This one. This print C. Second. Last line. Print C. No. Last line. That you put it on comment.
Comment.
No. Comment it out. Yeah. Now run it.
Vectorization is in 3 milliseconds, and in the for loop it will take 14 milliseconds.
Yes. See the huge difference. Okay, Jagan, just tell. Explain this.
Sorry, sir.
Yeah. So you show your screen. I'm explaining them. Yeah. Okay. So everyone, if you see the screen, so the same this particular code, if you implement, you will see this in a slide that we have shown. Import that numpy. Okay, and numpy array, that is np dot a comma b. If you see a and b has been randomly initialized. If you see a comma b, and if you compute the time, that is tick tock with the tick time dot time, and this import time, we have included that library import time, and if you compute the time, it will come something that is printed here. Okay, that is 3.003856 millisecond. This is the vectorized version. And the non-vectorized version, that is using a for loop, the same thing we implemented, okay, using a for loop, and see the time that has taken, that is 14.0011. So huge difference. Okay, almost here it is showing 4 times. But once you increase this number, that is, we have computed for 10,000. If you see, a equal to np dot random dot rand 10,000, b is also np dot rand 10,000. If you increase from 10,000 to 1 lakh to 1 million to 1 crore, the more the number you increase, the more difference in timing you will able to find. Here it's only a matter of 3 millisecond to 14 millisecond. In a vectorized version, it is 3, for loop it's 14. If you increase that range, you will see it's almost, going linearly. Okay, so the more you increase the range of computation, the more the time difference you will see. So that's the beauty of vectorized version. Okay. Okay, Jagan, so you can share this code with the participants. Yeah. Okay, I'm sharing my screen. Hi, Jagan. Hello.
I've copied the code in the chat box, sir.
Okay.
Even though I follow giving the file directly. Yeah.
Yeah, no problem, no problem.
It's there.
Okay, so here any question?
Yeah. Participation you can download the file. It is there in the chat box. Have a questions, I think, sir.
Yeah, please. I will be happy to answer. Yeah.
Sir, Dr. Srinivas, we can.
Yeah, sure. Hi, Srinivas. Yeah.
No, he is not responding.
Okay.
Rojamani, I'll give opportunity for the Rojamani.
Yeah.
Ma'am, you can. I'm requesting to you ask to unmute. Okay. I'll give on another person to Dr. Raj Kumar.
Okay.
Yes, sir. You can utilize.
Hello, Chandra sir, are you hearing me?
Yeah, I can hear you. So, have you seen the code execution of the code in Jagan's machine?
Yeah. I have.
Followed. You have followed it, right? Okay. I see. Yeah.
Nice session.
Yeah.
And sir, that in the last it came 0.0 vectorized version and loop version.
Yeah, that was finally the answer came like it was 3 millisecond and it was 14 millisecond. The non-vectorized version was 14 millisecond and the vectorized one came to about 3 millisecond when we took the data range in the in 10,000. So if you increase that data range, the more you increase, the more difference you will see.
Yes, sir.
Time of execution.
Yes, sir. Actually, I would like to add one point, sir. This problem I also faced, sir. When what happened when Python computes in a negligible time for let us say for 10, 100 objects, 1,000 objects, it is showing 0.0 millisecond only. I also got many times like those. I mean, when the data set is very low, 10 objects like that.
Yes, true.
It is showing, sir. That's why at that time also Python is computing correctly, sir. That is running now. We run that program to thrice or twice now. But it is doing correct only because if it is negligible time, it is show always 0.0 millisecond only, sir.
Yes.
As you said, now if it is very much increasing, it will show the difference not only linearly, sir. Sometimes it will go exponential also, sir.
Yes. True. I agree.
Because I tested for, sir, from 0 to some 50, 100 objects to up to 10 lakhs. I run into some competition, sir, when I am doing research. So it is
1 million. You tried till 1 million. Right.
I tried up to 10 lakhs, sir, because I have only some 1 GB RAM like that.
Okay.
So up to 10 lakh only some sample like this only some sample loops and like that I tried, sir. We can see very lot of difference, sir. If you go 10 lakhs and 50 lakhs, as you said, it's a very very nice and keen point, sir. If you, because the file size is more, then we will feel what Python
The
will
difference,
do. The difference will feel, sir. But for normal things, when we told to students also or anywhere, we never feel some for some 50, 100, like those objects we never feel, sir. But if the size is increasing enormously, we will feel, sir. What is that difference for a normal loop and what you said, that np dot dot np dot dot version, that vectorized version. Anyway, sir, very good information, sir. But now, due to some 45 minutes, there is a power loss here. That's why I'm unable to follow.
Okay, I'm sorry. Okay.
And in the meanwhile, I have remaining, I followed, sir. Thank you, sir. Thank you.
No problem, no problem. Any other doubts you can raise, we can come offline also, not an issue. Okay.
Can I give you opportunity, Rama?
Yeah, sure.
Yes, sir.
Sir, in the code,
yeah.
While executing in the Python notebook, they have written the statement inside the for loop, sir.
Okay. So, any bugs are there you have noticed?
While executing, you have written the last time in the for loop, you calculated the time starting before the for loop. The time completion you have calculated within the for loop.
Oh no, I think that he has changed, right? Jagan, you changed, right? It made outside the loop for loop.
No, sir. It is inside the loop, sir. That was I observed.
Let me share the screen, my screen, sir.
Okay, Jagan, then you can make that change, not an issue.
That is inside, sir.
Let me keep outside.
Okay, yeah. I think due to this indentation, yeah, right.
I can run the code. It's vectorized is showing to 2 milliseconds and for loop it's 15 milliseconds.
Yeah. Yeah, thanks for pointing it out.
Yes, sir.
Thank you very much.
Thank you, sir.
Okay. Okay, so I'll just move it to the next. This is the non-vectorized versus vectorized version, and this is how the difference it looks like. Okay, is u equal to a into v, and if is a matrix like the matrix vectorized implementation, and so this ui is equal to aij vi. Aij is the matrix where you fill with np initially with the zeros with the column vector, and then with I some range with j some range, and then you compute aij into v of j. That is ui plus is equal to aij into v of j. So this is basically what I would say, it's a non-vectorized version. And similarly, you can have a vectorized version in this way, np dot a comma b. This is a matrix. A is a matrix here, where not only we can apply to the vector, but also is the vectorized version of this matrix implementation. This is also possible. Okay, so so vectors and matrix we can apply to the exponential function also. So applying exponential function on every element of a vector or matrix. So suppose v is a column vector from v1 to vn, and this u is e exponential e to the power v1 to e to the power vn. So here we can write in a non-vectorized version like u is equal to np dot zeros n comma 1. So initializing with 1 is with zeros, and then with the for loop for I in range n, we can express this in this way. UI is math library. Okay, and then with this function we are using math dot exponential function in this library, math dot exponential v of I. Okay, we can write like this because this implements this particular. I'm just take my pointer, laser pointer. Yeah. So math dot exponential v of I. So u is equal to exponential e v1 until e vn. So this is math dot exponential vi. Okay, I is equal to 1 to n range. So this is the non-vectorized version. Okay, Now if I equivalent, if I write here the vectorized version, so how it will be looking like, import np numpy as np, and you can write like this: u is equal to np dot exponential np dot exp v. Okay, so very in a single line of code you can implement, okay, that how you do that, you apply the exponential function on every element of a vector or a matrix. This is how you implement with the help of a numpy array. Okay, so element wise it's also possible. V star star 2 and 1 by v, the element wise inverse, element wise square is also, everything is possible with this numpy. Okay, so the logistic regression derivatives, if we see here, okay, I think this particular part, vectorized logistic regression, and I think, yeah, we can, where we can implement, we can show this. Okay, so these are logistic regression derivatives. We will finish this today. So just try to recap. Just try to recap this particular thing, where we will see for individual. I mean, this is for M training examples. Okay, for M training examples, just try to recall the formula. It's very easy. Everything we have seen before. Just try to recall this. We need to initialize, okay, with np dw np zeros. We can initialize, and then we can start the loop where we can write like dw plus xi dz. Okay, so this is, we need to remove the for loops here. Okay, first we will see how to remove this particular for loop, then we will see how to remove this particular for loop in the vectorized implementation. So this we can definitely write instead of dw, because these are the features, dw1 dw2, w1 w2 are the, yeah, parameters, multiple parameters. So we can write these multiple parameters, okay, for a single training example in this way, because I equal to 1 to m means it's for multiple training examples, and for each training example these are the parameters encountering. Okay, now first we'll target this, how to show these multiple parameters into a single one. Instead of w1 w2, it can be wn, because for example I'm considering here a two layer neural net. So w1 is for the first, w2 is for the second layer. So instead of that, we are representing in a vectorized format that w1, the dw, instead of dw1 dw2, we are only using dw plus equal to xi zi. Instead of x1 x2, we are writing only x. Okay, then we will see how we, through this instead of these multiple training examples, I mean, how to represent the vectorized format of these multiple training samples in the next slide. See here, if you see the vectorized logistic regression. Okay, so as we know that x is for the multiple training samples. So x1 to xm, 1 to m, or for all the training samples, we know that these individual, the rows, how many rows will be there, the number of input features, nx. In the previous, I mean, the yesterday's discussion, we already had a discussion that the number of rows is xn, the number of input features, and the number of columns represents the number of training samples. So in this way, if we can write, okay, so how it will look like, say z, we know z is equal to wx plus b. So in a vectorized format, how we are writing, just try to feel the physical significance of it. Okay, so z is equal to z1 z2 until zm. Okay, and this wt, okay, wt, where wt, I mean, we need to compute wx. Okay, and wt is the transpose, w is the weights, and x, this x are the, from here you can get x, x1 x2 until xm. Okay, so this actually, this will be small x, basically this will be small x. There's a little bit printing mistake, this will be small x. So for all the training samples, okay, all the training samples are getting convolved with the w, that you need to keep in mind. wtx plus b is individual. So if you see b like one single real number for each training sample b, and for multiple training samples it is b1 b2 until bm. So this is how we represent the vectorized version of it, and finally we get wtx plus b is equal to z. Okay, one second, just put my battery. Yeah. So the thing is, this Z1, Z2 until Zm, we represent that WTX1 plus B, WTX2 plus B until WTXM plus B. Okay, where B is basically a broadcast. So if we add B here, it will add to every individual terms. Okay, so finally we get an output like this: WTX1 plus B, WTX2 plus B until WTXM plus B. So this thing, how we realize in a vectorized format, we write this formula NP dot, because these individual terms are nothing but Z1. Z1 is WTX plus B, Z2 is WTX2 plus B. In this way, Zm is WTXM plus B. So we write like this: NP dot of WT comma X plus B. Okay, and finally we get the activation A as sigma of this big Z. Okay, activation is sigma of this big Z, where activation A is individual AIs, A1, A2 until AM. Okay, so this is how the representation of this vectorized logistic regression of multiple training samples on the entire neural net. Okay, I hope this is clear. So now we will see how we do the vectorized logistic regressions gradient computation. That is also very important. Vectorized logistic regressions gradient computation. So just try to recall, in the previous lectures we have seen, previous slides, that dz is equal to a minus y. Just try to recall, dz equal to a minus y. Okay, things will be clear. See here, dz is a minus y. How we compute it? Yes, dl dz. Okay, yeah, dl dA is this, dA dz is this, and dl dz is a minus y. From here, if you recall, dl dz, that is dz is a minus y, dw1 is this, dw2 is this. Okay, dw1 is x1 dz, dw2 is x2 dz, and db is dz. So from here, try to recall. We will see here. Yeah, we will see dz is a minus y. So this vectorized representation, this z is the capital Z, and a is individual a's, y is individual y, there is a y target. Okay, and dz, capital Z is individual dz's. So from here, so we represent this vectorized representation as dz is a gradient. Why dz? Because it's, I am showing the gradient computation of this vectorized logistic regression. Okay, so this is dz is a minus y, where a, capital A and capital Y represent the small individual activation and the ground truth values, a1 y1, a2 y2. So in this way, and finally, like when we write db, we know that db is equal to dz, so we can write in a vectorized format that 1 by n np dot sum dz. Okay, so this is again, right, we can write in this way, that dw is 1 by m x dz, because we as I told, dw1, dw2 we computed previously. So how to represent that in the vectorized format? So dw is the summation, I mean average of 1 by m x dz. So it's a transpose, and x you represent in this way: m training samples and n feature vectors. So x1, x2 until xm, and dz is basically this x dz, as we know, dw x dz. So dz is this transpose, we can write it in this way, and this facilitates in this matrix multiplication. Finally we get x1 dz, x1 dz1, x2 dz2 until xm dzm. So this is nothing but the recapitulation of the already existing things whatever we have discussed, but in but this is the vectorized representation of this gradient computation. Okay, and finally here what we get is the same thing, no difference, the same thing how we do the vectorized representation of this logistic regression for m training samples. So this will be extremely clear if you see how finally after computing dz, dw and db, then how we update the values of this. Okay, this is a very simple representation. Once you go through this, you will be able to understand, because starting from Z to A to DZ to DW to DB, everything we have implemented here with the capital terms implements shows the vectorized representation. DZ, A, Y, all these are vectorized implementation. And finally, once we compute B, after computing DW, see DW here also all the like vectorized implementations. Capital X represented by capital X, capital Z. DB is this np.sum dz, and finally after computing DW and DB, how we update the weights. So this is the gradient descent update, okay, from this vectorized computation. So this core mathematical concepts, this core engine, if this is clear, then the other things will not face any other issue while we start deep diving into the neural net architecture, because these concepts are very primary and very significant to understand for any later complex understanding. Okay, any questions, Jagan?
Yes, sir. If you have any queries, please raise your hand. After session, sir, after queries, we'll wind up the session today. It's about 4:30.
Yeah.
Sir, someone is in chat box, sir.
Okay. Okay, so Jagan, I think this neural network architecture will start. Can we start today, or can start tomorrow also?
It's around 4:30, sir.
Okay. Then we can start tomorrow the neural network architecture, and then the CNN will start, and we can try to finish tomorrow, and one more half day we can take and can implement.
Yeah.